Okay, so it's 8:21, and I'm here with just loud in the lecture room. You see that I'm sitting in the lecture room 2209, but you guys are not here, and that's a major disappointment. Another major disappointment is the fact that I can only see that there is what was it, 6 participants in that stream. So that's a unusually low number. Maybe I wasn't clear in biomechanical lecture when I said that this Monday the lecture will be available live. Of course, it's always available in stream as well, but I was expecting you guys to sit here with me, but obviously you're not here today. So it's gonna be like this. So it's no screen, no that high quality stuff that I can do in my basement office, but it's gonna be something that look like this. And so what I'm planning to do today is that I will keep on discussing about the content modeling. And then there is something that is kind of like mixture of things that I would like to discuss with you. And the first thing is a stress evaluation, and then a little bit about what is that we could do with the stress information. And one of the things we can do is related to fatigue prediction. So once we know the stress histories in particular, then we can conduct the fatigue analysis. And the fatigue analysis is something that this university is kind of specialized to fatigue prediction and analysis of fatigue phenomena. And there's this laboratory of steel structures that is doing quite a bit of experimental testing regarding the fatigue life, and they're also doing some computation. So how is it we can support them by using a simulation? That could be the third topic of today. And then the final thing is the large deformations. And the large deformations, we'll see how much we have time to discuss about that. But this goes in this category of finite element method. Like I mentioned, I think that in the beginning of this period, there is one lecture which is a finite element modeling. More I was thinking like multi-physics, co-simulation based stuff, but now it's going to be large deformation, which is nonlinear finite element method. And then what happens on next week, Monday, again, I will be here in the lecture room. And I'm going to explain a summary and instructions how is that you can prepare yourself to midterm exam, and then master thesis work, and not part of the exam. This is my instructions to you, what makes sense you to do when you get started in your master thesis project. Some of you already may have it on, but even if you have it on, I think that there's a few instructions that benefits you, and those of you that haven't yet started, I think it benefits quite a bit. So that's what up today. And again, if you wanted to come to see me in the lecture room 2209, I'm here. But remember, keep the stream on if you decided to do so. Okay, so with this, few practical matters. First practical matter is that there is an open doctoral researcher position in University of Oulu. And this is a little bit a small font that you may have a hard time to read it, but if you Google University of Oulu doctoral researcher position, and if you put this physics-based simulation, I think that you're able to find it. This position is related to project that we cooperating with University of Oulu. And in this project, the idea is to use artificial intelligence-based algorithms together with the multibody system simulation. And why is it we wanted to do that? That's simply because artificial intelligence is, most of the artificial intelligence algorithms, they need an awful lot of data. So much data that it's inconvenient to produce this data by using experiments. But what you can do then is that you can use enhanced computing. You can use efficient physics-based computing to produce the data that is needed in artificial intelligence. And that's exactly what being carried out in this project. And why we want to do it? Because we would like to automate certain operations and certain features of mobile machineries. And of course, the big dream is to make them fully autonomous. I don't think that it's going to happen. I mean, the fully autonomous most probably not going to happen in this 2 years project, but there's going to be fundamentals that are then later used to make the mobile machinery to be more autonomous or have more automated operation actions and stuff like that. Okay, so that's opportunity. And the professor in Aalto University is a former team member from LUT, Professor Emil Kurvinen. So I think that will be a lot of fun. Good position to consider. So take a look. Please consider. I think that I'm not sure, but I think that Emil would like to have a person that is already holding a master degree. There may be possibilities to do your thesis project as a part of this project here too. But go and ask from Emil. He knows the details. All right. A little bit of what is it we have discussed so far in this fourth period. So we discuss about BLM technology, and we discuss about the biomechanics and bicycle dynamics, and we also discuss about the content modeling. And now there's a color coding in this slide, and the color coding means that the color in green, means that these are the subject matters that we will keep on discussing in this fourth period. And the ones that are color-coded as a gray, those are the ones that are already completed. And now this figure is put in a kind of in a coordinate system where the x-axis refers the level of expertise. So level of expertise meaning like how good you need to be able to apply or need to be able to be active in this particular field. And then the y-axis is like how well it can be applied, and how well it can be applied to a wide variety of different applications, mainly industrial applications. And you see that the bicycle dynamics is a little bit limited. It's not just the bicycle. It can be applied in a certain way. It can be applied to other vehicles too, but still it's nowhere near as wide as biomechanics. Then BLM in term is something that is actually needed anywhere you go. Anywhere, if you decided to go to industry, for sure there will be one way or another that you need BLM systems. And that's something that the lecture itself was a like overview. And sometimes I was struggling to get the concrete things like how it actually works. And I think that the idea was within this 2 hours lecture to get just an overview. And if you want to learn the details, then it's highly recommended you to participate the courses that are specialized to BLM systems. And I think that those are the ones that if you decided to select this digital engineering special area, there is at least 2 courses that are coming from industrial engineering department. And those are the ones that are heavily recommended you to take. Then moving on, then the content modeling is something that is needed wide variety of applications. So it's needed in vehicles, it's needed in games, it's needed in many other applications, and it needs quite a bit of knowledge to be able to be good in that field. That's something that we will continue to discuss in today's lecture. Stress evaluation is again something that can be applied in a design processes. Not so much about I don't see how well it could be used in a production or online monitoring. It may be this machine maintenance aspect. It may be in service business. It may be some use in that, but other than that, so I don't see how it can be used in any other product processes other than product development. Then the nonlinear finite settlement method, which is this large deformation thing, that's going to be something that can be applied. A lot of different things you can learn, like you will learn today. And you need quite a bit of studies to be able to do something in that field. So that's a little bit an overview. We will get back to this overview. Let me just check there, my coffee. So I will get back to this overview on Monday, next week Monday. Okay. contact modeling. So let me jump, I think that it is here, a bit more further in this video. I think that it is somewhere here. Where is it now? Examples about the contact descriptions. You know, this is this video here is representing kind of like the system that is used to teach the operator of different kind of cranes to learn how to move different products from harbor to ship and ship to the harbor. Let me see if there is no contact description. I think that this is the one that it gets started. This guy, I think it is losing the package. And you see that the package is then, yeah, like there. The package is then headed to ship. Here too is a contact between the container and the ship. And we will continue to discuss about this contact description today. And we already learned that there is this very often used technique, which is based on the penalty forces. And today we're going to learn something a bit different. Okay, there are the contacts between the container and crane itself, container and the ship. Let's see how this is okay. So there is no, and again, but there is still a contact, of course, you know, because you need to locate your container the proper position, and that is modeled by using a different kind of contacts. Now, this is a summary from what was it? 4 weeks back. So 4 weeks ago, we discussed about the contact modeling. We concluded that this consists of 2 different steps. And the first step is a contact detection. Contact detection is something that typically is the one that takes quite a bit of CPU power. So contact detection is, like title implies, detecting where the contact takes place. So there have to be some kind of clever algorithm to do it, because there's no way that you can use some kind of if-then modeling approaches. And if-then meaning that you're describing every single possibilities how the contact can take place. Because those possibilities, there's a lot of them, and makes no sense to do this way. So the algorithm is needed to do this contact detection. And then once the contact itself is detected, so you know that there is 2 bodies colliding, they are having the contact, then the next step is a contact event modeling. So how is it you can prevent these 2 bodies to penetrate, or you may allow them to penetrate it, but not too much. So this is a contact event modeling. And we concluded that contact detection very often used, or actually the dominating approach is a bounding box method. And the bounding box, there are different varieties. How is that you can put your bounding box around or top of the body itself. But anyway, so it moves, the bounding box technique itself is based on the different levels. So there's a root level, roughly speaking, the big box that is surrounding the big object. Then the branch level, which is a smaller boxes surrounding the smaller object, and the leaf, which is like drawing primitives. That's the final. And now you see here, this is a good example. This box here, you see the biggest possible box. That's the root level box. And you see that inside of this root level box, there's a branch level boxes. Here is one. These like lids here are another branch level boxes. This one here is a branch level box. So you see that the root level box is including quite a good number of branch level boxes. Then these leaving or these drawing primitives are not visible in this picture. But that's how it goes. That's how it goes. Let me see. Let me just see how healthy is my screen. My streaming here seems to be okay. How many participants is in a stream right now? Can you already see that? Oh, 6. I think it is still. Isn't it 6?
Yeah.
Okay. All right. Now, contact description. 2 different ways to do it. So we already covered the penalty forces. And then another one is using these inequalities. And in these inequalities, we're going to use a method that is called cone complementary approach. The cone complementary approach itself is a kind of a own world. Needs quite a bit of effort to explain all possible details related to this other opportunity, which I'm not planning to do it in this class, as this will be a subject matter of entire class. And I'm going to just give a highlights, like what this is based on. But the penalty forces, that's something we discussed 4 weeks back. And the penalty force is simple like this. So you computing the force that is separating the object based on penetration. So you're allowing rigid bodies to penetrate. And this penetration of rigid bodies is called indentation. So it's like indentation, which is kind of like a description of their flexibility, which is weird because rigid body is not a flexible, but because they are able to penetrate, this penetration can be considered as a kind of a flexibility. It's indentation. That's what it is. So let me see how well if this is visible. So if I would have here a rigid ball, let me see. There is quite a bit of delay, so let's see how well this appears. Looks okay. All right. So this ball here is hitting to this ground, and now this is a rigid body. This body cannot deform, so its graphics always stays in the same form no matter what. But when this ball is hitting the ground, what happens then is that it is assumed to be like situation like this. Let me take this one off first. So it is intended to be, or is it matching to be like something like this? There is a ball again. And now, this one here, which is touching the surface. Of course, what happens is like this. This is the indentation. That's what is called in English indentation. And that's what this penetration here. This is an X here. And now, based on the penetration, you compute the force that is moving or shooting this ball off of the ground. But now, this kind of means that, the actual body deformation, or the kind of how it is imagining that the ball will behave, is like kind of like a flexible body. And that's what it is. This penetration is kind of having certain physics-based approaches. Now, like mentioned here in this equation, we have here x, which refers to penetration. Then we have here k, which is the stiffness. And then we have here n, which is showing what's the power in this equation. Sometimes, actually quite often, there's another component in this equation, and another component is damping. Damping is quite often used because this easily becomes to be quite violent situation when you have a force that rapidly pushes the ball away. And to make it more stable, computationally more stable, and also a little bit more physics-based, there is sometimes a good idea to have a damping on it. You just need to be super careful because certain damping models are damping the motion when ball is moving this direction. But they're also damping the motion when ball is moving this direction. And that's not possible. That's not physically possible. You understand that if there is a penetration, indentation like that, then there may be a damping here. But when the ball is moving away from the surface, there is no way that there can be any kind of damping in this case. And the worst possible damping models are such that just when the ball is shooting out from this grounded surface, the damping gives it, or kind of take a hold of the ball and put it back in the surface. And that's very unrealistic. But this is just for your information. Now, this x here, the n here, the power n, it's quite usual that the n is not 1. And is not 1 because if it is 1, then there's a discontinuity just when the force is introduced from 0 to non-zero value. And this is computationally always inconvenient. So if there is a n other than 1, let's say 2, 1.5, or any other number, then there is a kind of smooth curve from zero force to non-zero force, and this is something that is highly recommended to do in modeling perspectives. Okay, now this another approach, this complementary approach. Shortly speaking, the concept is this. So you have this ball, and you have the ground here. And what you're going to do then is that you will create the constraint equation. Constraint equation that says that the ball can do whatever it wants, so it can go whatever place it wants, except it's not allowed to penetrate through the surface. And now let's say that, you know, there is a, let's say the measure some kind, let's call this measure as a t here, randomly t, and now this measure is made in such the way that, you know, we're gonna build this constraint, which is a function of the t. We're gonna say that this constraint have to be always equal or more than 0. So this is inequality. You see that this is a constraint which is having the very different nature than the ones that we have used before, because previously all the constraints were something like equal to 0 or something else, and now we have inequality. Now that's how it works, roughly speaking. Now what then happens to this inequality? Well, this have to be taken into account as a part of the equation of motion. This is going to be a little bit of an involving process to take that into account, but roughly speaking, it will be treated a little bit the same way than this constraint equation. And then we're going to have a possibility to describe the contacts. This one here is a use of inequalities and complementary approach is a very efficient approach where you're describing large number of contacts. A large number of contacts means that if there is not just a single ball, but thousands of balls, then use of these penalty forces becomes to be very inconvenient and very unstable as well. Because remember, if there's a lot of balls, there's a lot of penalty forces, and if the penalty forces started to somehow fluctuate, that can cause a chain reaction, and the chain reaction end up to be the situation that the balls are exploding, or the pile of the balls is exploding, and that's, you know, that's very much unrealistic case. So let's take a look at the details. So here it is. So we have, like, here is this constraint that was mentioned. This no, I don't remember what this is. I think it is a phi constraint. So it becomes to be active if the phi is equal to 0, and that's roughly how it works. There is a paper that I can put it in a model database, so you can take a look about the basics. How is this method? But here are the inequalities. So we are dealing with this kind of inequalities. We put these inequalities as a part of the equation of motion, and that's roughly speaking how the system works. Here's an example. And you see this is, don't know how many balls is here. I'm estimating like could be less than 100, maybe 50 balls. And they're dropping and they have the interaction between each other. You know, there's still obviously not things correctly modeled, because you can see that this sea of balls is boiling a little bit. It shouldn't be having any kind of motion once they are settled. You see here, you can see a little bit of like jumping back and forth. Yeah, like something like that. Maybe because it seems that one of the ball is rotating, so maybe that is a reason. Yeah, this one was rotating quite seriously, which looked like this. You cannot see this in reality. But anyways, that's what this is based on. Now, let me introduce my friend to you. And my friend name is Dan Eckert. And let me see how well I can play this to you. Now I'm not sure if I'm gonna put this on. If you can hear, let me check from desktop audio. Okay, I will mute myself and we'll put the desktop audio to be active. Okay, that seems not to work. So let me try again. Maybe I can instead using where this goes now. Display speakers.
Of this vehicle. In this case, this is a project that we have with the JPL, and you have a vehicle with the Good afternoon. My name is Dan Edruth. I'm an assistant professor at the University of Wisconsin-Madison, and I want to start by thanking you for taking the time to attend my presentation here. I'm going to talk about this topic of taking the leap from multibody dynamics to many-body dynamics. And let me first tell you what multibody dynamics is. In general, multibody dynamics looks, for instance, at the motion of this vehicle. In this case, this is a project that we have with the JPL, and you have a vehicle with a relatively small number of parts. What makes this a many-body problem is when you start looking at the granular terrain that the vehicle moves over. And in reality, what they're interested in, they want to see if this vehicle gets stuck in the sand. Now, in 1 cubic meter of sand, you have about 1.5 billion particles. And although you don't see this in this picture, in this movie, sorry, those small parts, they move. And you solve some equations of motion, and they come back to tell you at each time that I don't move, I don't move, I don't move, I don't move. Once in a while they move, but nonetheless you have to solve at each time a very large problem. Now, this is a simulation that is about probably 2 or 3 years old, and I showed it to some army guys, and one of them raised his hand and said, so why is that Mars rover moving over potatoes? Are there potatoes on Mars? And you know, this is my point. There are no potatoes on Mars, but you cannot go today to very small dimensions for granular material, because if you have, for instance, like a commercial off-the-shelf package, and you run a dynamics analysis, multibody dynamics, classical multibody dynamics analysis, with 32 balls dropping in that bucket, and you look at the time evolution of the system, it takes here for 32 balls about 600 seconds to understand the dynamics for 3 seconds. And not only that, but if you look at the shape of the curve, it's a quadratic function that describes this dependency, and a very quick back of the envelope computation tells you that if you have 1 million particles, it takes for 3 seconds simulation about 25,000 years to run that analysis. And you know, with all this Medicare discussion and cuts, I'm not going to make it that far. So we need a different solution here. So this is the solution here. We change the math behind the formulation, and this is a system that has about 1 million parts, and they're moving, and we're tracing the motion of every single particle and how it collides with any other particle in the system. And there's like a ball of a lower density material, and it flows on that. So here is classical multibody dynamics. I'm not going to get into the details, but there was some math, okay, going from multibody dynamics to many-body dynamics. And once you do take care of this problem from a different mathematical formulation, all of a sudden it becomes feasible, okay? And when it becomes feasible, then the next thing that you want to ask is, well, how close do the results come with respect to reality? And here we have like a silos, like a flat hopper simulation, and we ran that simulation, and then in the lab, we went and we took something similar, a graduate student, low salary, filled it up, painted the balls, and we did that simulation, and then you put them side by side, and here's what you have: experiment and simulation, and they look pretty much the same. And we did some other simulation, but I'm not going to show the results here. Of course, if you look at this problem, you have millions and millions of bodies that move. Now the beauty of it is that basically they all move the same. So there is a lot of scope for parallel computing in this. And this is where you can use, for instance, GPU computing or multi-core computing. And this is what we did. And we implemented, for instance, here you have a system that has about 500,000 parts. And this is a project that we work for the Army. And they're interested in how the terrain deforms on a track vehicle. And it took about, for 18 seconds of simulation, it took about 1 day to carry out this analysis. Now, you can go beyond that, and I have to tell you that, I grew up in a communist country, and it was like, food shortages and such, so one of my recurring dreams was like, eating lots of chocolate. And here is it, I can say that I'm a happy man, my dream came true. Either it's like a virtual world, I could have lots and lots of like chocolate here. Now the tricky part about this is that it is a simulation that combines multi-domain physics simulation. It solves at the same time the Navier-Stokes equations and the Newton order, and designed in a parallel fashion. And if I were to conclude, this discussion, it boils out to one idea. There is a lot of computational power today, like parallel computing and such. It takes new math that you can map on that parallel architecture, and wonderful things happen. And with this, I thank you again for taking the time to attend my talk.
Okay, so quite many things to learn from that. First of all, there was this new term about many-body dynamics. It's not well-recognized scientific term, and it's hard to tell when the multi-body changed to be many-body. But what he's referring with the many-body was to use this complementary theory to describe the contacts. And that makes it possible to deal with a huge number of bodies. And the huge number of bodies is, let's say, more than 1,000. Maybe that's safe to say that that's many-body. That's no longer a multi-body. And he mentioned something, other interesting thing too, which I have not discussed earlier with you. And that was the problem that, there was this tank. I don't know what's the military tank weights. It's like a 60 ton, something like that. And then the sand particles, how much that weighs? That may be 1 gram. So the weight difference is huge. And the weight difference is something that makes it difficult to deal with. And this particular is the case when you're using these penalty force approaches. So if you think about the 60 ton is in a surface of sand particles, how challenging it is to compute it in a way that it is numerically stable. That's going to be a big challenge. And another thing was that he mentioned that the computational power needed increase exponentially, and that's another big problem. And that's something that is not the big. Is not scaled in the same way when using this complementary approach. So that's for your information. So now you know what's the many-body dynamics. You know a little bit about what are the difficulties associated to these mass differences, and that's about it. That's what I'm about to tell you today. Now let's move on. I see that time is running and it's already 8:55. And the next thing that I would like to shortly discuss with you is a stress evaluation. Stress evaluation, which is, stress, that is like one of the fundamentals needed in when you're conducting the structural strength analysis. So you need to know how much stress is imposed to your structure. And now, can we get this information using the multi-body system dynamics? And we can. And there are actually 2 alternative ways how that can be obtained. And these 2 alternative ways I'm going to introduce you to next. And then, like mentioned also in the beginning, then I'm going to use this stress evaluation to conduct a fatigue prediction. And this time my explanation related to fatigue is related to welded structures. Oh, what is this? I need to put this sound off. Okay, stress analysis based on multi-body system dynamics. So like I said, 2 different alternatives, 2 different ways to do that. And these 2 ways if goes directly to business, are showed here. So we could take the forces, loads, well, forces actually, and the forces are external applied forces, inertia forces, and we can extract those forces from multibody system dynamics, and we can create the load cases based on those forces in finite element software. And it's basically, if you can still see my writing here in a blackboard. If think about, where was this white one? This one. So this is our equation of motion. If using this method based on Lagrange multipliers, this becomes to be a little bit unclear. Now, this representing the forces, external applied forces and inertia forces. So we can, and reaction forces, of course, because the reaction forces are the ones that are associated with the Lagrange multipliers. Now, these are all the forces we can take and build the load cases for the finite element model using this information that we're solving from multibody system dynamics. And this is very rough approach, because this approach typically assumes that multibody system dynamics is conducted by using rigid bodies. And these stresses and deformations are like superimposed afterwards, like a post-processing technique, but they are not affecting the actual computation of multibody system dynamics. And in that perspective, is not that much in the use at the moment. This is one of the first ways to describe the deformation in multibody system dynamics. And this is something that, if you look at the old books from the multibody system dynamics, you can find this very sophisticated term, which is called linear theory of elastodynamics. And that sounds like fantastic. Sounds like, oh my God, that have to be something super complicated because it's such a nice name. And it's this one. It simply means that you conduct your your multibody simulation, you get the forces, and then you take those forces and you're building the load cases to your finite element model. And then afterwards you get the deformation and stresses. Because in finite element, then basically it's like this. Particularly if I look at the static cases, so it's like this kind of case. So I have here displacement that I'm solving, and these are all the forces that apply. And this allows me to describe these displacements. And from displacement I can get to strains, and from strains I can get the stresses. So that's how it goes in finite element method. And typically, when you think about the dynamic equilibrium forces, all the forces are in dynamic equilibrium. So they should be able to tell the equilibrium situation. So you can take those forces directly, you can put them here. That's the way to go. You solve this displacement, and that's what is called linear theory of elastodynamics. Easy to say, more difficult to do. There are a lot of complications, including the fact that, even though that this equation is in dynamic equilibrium, it's not in a dynamic equilibrium, because the minor differences between the different forces leads to the situation that this equation is actually no longer in equilibrium. And to make it in equilibrium, you have to introduce some kind of boundary conditions. Let me just highlight this in a simple example. So you have, let's say that you have very simple dynamic system here. You have, let's say, the pendulum. Let's make it even easier than that. Like just a beam like this. And there's an external forces applying in a system, both sides. And let's say that this force is a little bigger than this force. F1 is a little bigger than F2. So this is moving a little bit on left side. How is it you can handle this kind of motion in your finite element model? That's going to be very, very hard to do. There are, of course, inertia forces that are somehow compensated, that in equation of motion. But how are you going to do this in your finite element model? So it's going to be very hard to do it. So, and you have to introduce some kind of boundary condition. And that makes it very inconvenient to use it, because these boundary conditions in general case, are extremely difficult to figure out. So that was the first approach. The second one, very nice, and something that is currently much in use. And this is based on something called modal stress matrix. And basically, it uses the fact that you're describing your bodies as a flexible bodies in multibody system dynamics. And once you describe your bodies as a flexible bodies, you get these modal coordinates. Remember? You get these modal coordinates that are describing the deformation. Modal coordinates, using the modal matrix, you can get nodal displacement. And from nodal displacement, you can go to strain, and from strain, you can go to stresses. Everything this can be made automatically as a post-processing technique in multibody system dynamics. So that's another approach. Drawback is the fact that the second approach forces you to model your bodies as a flexible bodies. That slows the computational, burdens the computational efficiency, but other than that, it's okay approach to go. Okay, so here are these details about the first step, which again is called linear theory of Alloster dynamics. You don't see this often anymore, but if you look at the old literature in the multibody system dynamics, you every now and then you hear this linear theory of Alloster dynamics, and that's what that refers to. By the way, there is a little bit, this takes you back to what happened 25 years ago. When you take a look at my doctoral dissertation, that was the dissertation that there was an idea to compute the stresses out of the multibody system dynamics, and there was a enhanced method from linear theory of Alloster dynamics. No one's wanted to use that anymore, but at the time that was the way. That was something that felt like good idea. Is no longer in use. Okay, so that's how it is. So you have your multibody model, the one that is here shown in right hand side. You take the forces, including all the forces, inertia, reaction, and external applied forces, and you're building the load cases, and then you're computing awful lot of static analysis, because every time step you have to solve by using a static analysis. That's quite a bit of work to do. Even though that you need to just invert your stiffness matrix once, but still is quite a bit of computing to do. Now, this is something that if you model then your structure as a flexible body, then this is this advanced technique that is still related to linear theory of Alloster dynamics. So forget about that. Now this new method. This is the equation of motion used when you're describing your bodies as a flexible bodies using the floating frame reference formulation. In the floating frame reference formulation, one of the unknowns is here, which is a modal coordinates. Now, modal coordinates are solved in position level. And once you know them in a position level, then you can get the nodal displacement, meaning like how much each of the node locations are moving and rotating. Now, this is an information that you can then use, like it is shown here, to extract the information associated each one of the elements in your structure using this kinematic matrix B. You can go to strains, and using the matrix of elastic coefficients, you can go to stresses. You put all these steps together, and this is called modal stress matrix, and it takes you from modal coordinates to stresses. Simple like that. Modal coordinates to stresses. Very sophisticated, very efficient, beautiful method. But it's not so easy to use in a sense that you need to make sure that your deformation is correctly described, because if not, this P is correct, of course the stresses are not correct. That's the kind of the disadvantages associated to this approach. Okay, summary is here. The first approach is a little difficult to use. It needs quite a bit of some CPU time. The second one is elegant, easy to use, but it forces you to model your structure by using flexible approach, floating frame reference formulation to be more specific. Okay, so that's about the stresses. So now, let's say that you get the stresses, you get the stress history. What is that you can then do with the stress history? And now here comes, so there will be my first in-class quiz of today. And I guess there's not going to be a lot of exciting things because we only have 7 viewers in our YouTube channel. But anyways, so fatigue analysis. That's what we're going to discuss next. Now, fatigue behavior ranges a difference significantly depending, are we discussing about the welded structures or non-welded structures. Now, most of the applications we've been discussed in this course so far are related to mobile machineries. And in a mobile machinery, the most severe problem is the one that is related to welded structures, because the welding is still a dominating way to put together heavy machineries. So if you want to combine the different components together, economical way to do that is by using a welding. Now, welding is a big problem in terms of fatigue. Why? That I would like to shortly explain to you, and then I would like to show you how is it you can conduct these fatigue analysis. Now, well, this says, what is needed to do this fatigue analysis. So you need to know geometry, which is like what kind of detail you're looking at. How is that you have welded these different components together. You need to know something about the material. Well, often we're speaking about steel material, maybe aluminum. That's about it. Those are the two choices. And then the loading must be available. Now, out of these 3 items, the loading for sure is the one that is the most cumbersome to get. That's painful to get. Because think about if you have a machine, any kind of machine that you have, make a blueprint, but you don't have a real structure available yet. How is it you can get these loading conditions? And how is it you can get these stress histories? Well, you can make a thought that you can make some planning, or maybe the machine is used in this and this way, and maybe this is how the stress history will be accumulated. But it's very cumbersome work to do. And that's where the simulation comes into play. So you can actually monitor the stress history while simulating the structure, and you can put this monitoring as a part of the real-time simulation. And that's going to be very convenient. And then while you are testing how your system feels like, you can get these very valuable data related to load histories simultaneously. Okay, well, this is basically said that the load is difficult to get. Fatigue, something that is very important to understand. Fatigue is a statistical phenomenon. So it's not possible to say that every single machine will break after certain hours of service. That's not how it's going to go. But there's a certain number of failures that will happen in a certain possibilities, and that tells the nature of the fatigue. So if you have a bad luck, it can hit you, and if not, then most of the cases it's going to be okay. All right, now fatigue, in case of welded structure, is different than non-welded structure, and the reason is there are actually 2 reasons, and the first big reason is the fact that, whenever you're welding components together, the welding process itself will introduce initial cracks to your structure. And this sounds like not necessary, how there can be initial cracks, because if the machine is brand new, there's no cracks. And you don't see the cracks. Of course, you don't see it, but if you take a microscopical, very close look about welded toy, and the welded toy is, here is one plate, another plate, and these 2 plates are welded together here. If you take a really close look in a welded toy here, you can see that every now and then there's like a very kind of a unpleasant small crack here, which serves as initial crack. So it's safe assumption to say that whatever you get, the new product, brand new product, that is full of initial cracks. And that's why the fatigue life of a welded structure is dominated by crack propagation. So you just need to handle the situation that there's a crack is growing inside of the structure, and you just handling or mastering the crack propagation. That's about it. Final fraction takes fraction of the second. That's when the crack is so large that the structure is no longer able to hold the load and it will be cracked. So that's what it is. Final fraction takes in a fraction of the second. Crack propagation is the one that is dominated here. Initial or crack initialization in a welded structure is not there. Is not there. In unwelded structure is very important, and that takes quite a bit of time. And usually, like the typical examples about non-welded structures are machine engine elements. Like you see, if you put your engine in a part, and you can see that there is a crack in your connection rod, for example. It's done then. So you shouldn't put back that to your engine anymore. But in a welded structure, that's a different story. And now here comes my first in-class quiz, which is easy. And says in welded structure, the fatigue life is dominated by crack propagation, crack initiation, crack propagation, and final frac. So those are the different options. Now let me show how is here's my Socrates. Squeeze on, this one. This one. Are you good to go? It seemed, by the way, I never realized that watching the YouTube from using a mobile phone takes an awful lot of battery. The battery dies almost immediately.
Okay.
Huh. Don't know why. Maybe this is such a heavy stuff. Maybe that's what explains it. I don't know. Okay, so I got the answers. So let me move this a bit. Here. 2 answers so far. I will get back to that momentarily, but please note that there is a Socrates on 3 students. And still it looked that I only have 7 views in my Socrates, no, in my YouTube stream. So rest of, okay, now I got 5. We'll see how it goes. Okay. Another problem, even equally severe problem associated to welded structure is the fact that welding process introduces an awful lot of heat to your structure locally. And because of this awful lot of heat that is introduced, there's quite a bit of residual stresses in your structure. And actually the residual stresses at the location where this crack is located at is roughly in a yield stress. It's roughly in a position where this linear stress turn to be nonlinear. This is where the linear deformation moved to be plastic deformation. And that's very bad combination. So you have this initial crack there, and then you have very high residual stresses. Because the high residual stresses means that locally, when you introduce just a little bit of loading to your structure, you immediately step here from linear range to nonlinear range. Immediately, more or less immediately. Okay, what is that? What that means then? It means that there's a plastic deformation. Very locally. Again, very locally. This is something that is confusing because when you look at the big picture, you see nothing. You see absolutely nothing. But when you look at this microscopical behavior, you have the plastic deformation locally. And this is a very lethal combination. And now let me take myself back to the Socrates. Where is it now? This one here. 5 answers. I'm going to close this. Maybe this is going to be, if this is 100%, so this is not accounted. It's not accounted because we have 2 little participants. So the threshold value for us is 10 participants. 10. Have to be more than a 10. So even if this is 100%, I'm not going to smile. I'm gonna smile. See, this is still 100%. Oh, very nice. 100%. Okay, but again, no dancing, nothing like no stupid thing. Like I promised that I will do the dancing, and I don't even remember what is that I promised to do if you guys scoring the 100%. Why not? Because not enough participants. Okay, back to this. Okay, now residual stresses. So we have this combination. So we have initial crack in a welded toy, and then we have high residual stresses. So meaning like as soon as you start loading your structure a little bit, microscopically, there's a plastic deformation. And that's what allows the crack to crawl. And that's how it goes. Now, the answer, sometimes you can hear, okay, all right, so we have a fatigue problem. So let's use a better quality steel to solve the problem. High strength steel. That would be the way to go. It's not going to help you. And the reason is this. That always, practically always, these residual stresses are exactly in the location where the linear curve changes to be a nonlinear curve. Doesn't matter what is this like high strength steel, this point is here in the higher, but still because of the residual stresses, it simply moves higher here. So it's not gonna help you. So if you have a high strength steel, then it means that this linear range here is longer than in a conventional steel. But because amount of heat introduced due to the welding process, you will have a residual stresses that are exactly in the point where this linear curve is turned out to be nonlinear curve. No help. So the high strength steel is not the way to go. All right, so how it goes then? This picture includes quite a bit of information, so let me walk through this picture with you. This shows okay, once we get the stress history, and the stress history is typically something that look like this. This is a stress, and this is a time. And then it goes like this. So how is it you can conduct the fatigue analysis based on this? Well, fatigue analysis is always about the delta sigma, the delta stresses, how much the load is imposed to structure and how much they are taken away. So it's very important to understand what is the stress ranges, delta sigma. This is something that you have to compute based on the stress history. Okay, so now you have this history shown like this. How is that how much the load is, put it in a system and take it off? Because that combination you need to figure out. Not just, if you put a lot of load in your structure and you keep it there, that's not going to be too risky business. But if you take your load and take it away, this kind of fluctuation is dangerous in terms of fatigue. How you can figure out this fluctuation based on the stress history like this? Well, you can use something that is called rainflow analysis. And the rainflow analysis is a procedure that you kind of consider that the stress history is a container. You have a container this shape, and you put the water to this container. So it's not the crate container, but you can see that, if you put the water to this container, it's going to be the water that goes to roughly this level, the water this level, and this level. So this is going to be looking when you use this as a container, and you put the water to this container. And then what you're going to do then is that you start taking water away from the container by opening kind of like valves top up at the bottom of the container. Let's say that there's one valve here. You take water away here, and you look how much the water level goes down. So it goes down here to here. So this is your first delta sigma. So the water will be still here, but it's gonna disappear here completely. So that's your first delta. Second one, you put the valve here. The water will go down this much. Here's your second delta, okay? Then here you put the one valve here, so it's going to be one kind of small delta here. Here, very little water will disappear. And here's one more delta. So now you've got the collection of deltas. And now, based on this collection of deltas, you make a statistics. Okay, so there's a different size of deltas. Let's say, let me put it like simple table here. Delta, which is, let's say, 100 megapascal. Or something like that. You count it, okay, there is a 10 times like that. Let's say 3 times like that. And then delta, which is smaller than that, let's say 90 megapascal or something like that. There's a less and less amounts like this kind of ranges. And then you computed what is an equivalent stress loading based on this stress history. So it meaning that every single deltas will be replaced by one delta, which is roughly the same, having the same damage than the number of small ones combined together. So this is called equivalent delta. This is needed because all the fatigue analyses are finally made against the experiments. An experiment is so hard to do the experiment that there's a wide variety of different kind of deltas. That's going to be inconvenient to do. So they always wanted to keep the delta to be equal. That's why you have to replace this number of different size of deltas by one, but it's roughly the same level of dangers than all these small ones put together, once you put these small ones together. All right, and then you're ready to go your fatigue analysis. Your fatigue analysis, how you can do that? Well, before you're able to do your fatigue analysis, it's important to understand that, again, when you take a microscopical look to your welded toe, the stresses are a little bit singular. So there's a quite heavy local stresses. And these local stresses are because of the local geometries. And now when we conduct a multi-body simulation, we cannot figure it out these very detailed stresses. And these very detailed stresses are needed if you want to use sophisticated fatigue life predictions. But we are unable to do that because we can only see the stresses that are keeping the structure in static equilibrium, but not more than that. We don't see like how much these minor discontinuities here are increasing the stress levels. We can get this by using a finite element method or some kind of other computing, but it's very important to understand that your fatigue element analysis depends on what level of stresses you're capable to get. And in multi-body system dynamics, it's the lowest level stresses you can get. You cannot account the stresses because of this local discontinuities. You cannot get the stresses because of this crack inside of your structure. These are the stuff you cannot get. And this shows a little bit like what are these different methods. So the first one, which is this nominal stresses, the one that is keeping the structure in equilibrium, that you can use. And you may go some more advanced approaches as well. You can use a hotspot method or fraction mechanics, but that needs some additional computing, something that you need to get it from literature, or you need to build your finite element or boundary element model by yourself, or you need to conduct the measurements to get these missing parameters. But roughly, when using finite multi-body system dynamics, we're limiting ourselves to first most coarse method. So this is not very sophisticated, but most of the cases it will do the job. Okay, that was a highlight about fatigue. Not yet. Then there's an example here. This example I like a lot because this is a crane that is still in use in our laboratory. So this is a crane that consists of 3 hydraulic circuits. There's a lift cylinder, swing cylinder, and turning apparatus, which is also hydraulically based. There are 4 flexible bodies and the mass is 370 kilos. And then this is moved to use, this mass is constant all the time. And here is measurements that are conducted using this crane, and this is a simulation model. Why is that I'm showing this to you is because this. Take a look at this guy. Okay, let me try to make it bigger. This one. This guy here. Well, it's not clear, so it's kind of blurred, but it's me, 100 years ago. And this is when I did my, this was a part of my doctoral dissertation. At the time, there were a total of 2 doctoral students in, well, I cannot say in the entire of mechanical engineering, but at least the ones that were more focused on the design. And at the time, it was not common to produce several dissertations in the entire university. Today, the situation is very different. But anyways, my doctoral dissertation was a part of this crane and part of the fatigue life prediction. And this shows like how is the stress history measured and simulated in 2 different locations of this crane here. And you can see that the prediction is amazingly good. So it's capable to make, it misses some of the peaks, but most of the peaks is very accurately predicted. And this is kind of quite surprising that it is this accurate. And now, what was figured out, that this design that still is in use, there was some clear misunderstanding the way the hydraulic pipes were lead to this swing cylinder and also this telescope cylinder here, because they were connected to this main arm by using a simple welded stud here. Welded stud. Remember what I just said about the welding. So welding is a dangerous thing, the dangerous business to do because of the 2 things: initial crack and high residual stresses. And because of these 2 lethal aspects, you want to take your welding away from highly stressed areas as much as you can. And definitely you don't want to put anything like it's more like decoration to something that is a highly loaded area. And this is exactly how this design was made. Look at this, it's just, to make sure that the pipes are connected. You can put this connection anywhere you want. But definitely you shouldn't put these connections in a location that is highly loaded. And you could put it here or here, doesn't really matter, but not here. This is the worst possible scenario you can put it, because they are playing not any other function than just leading or making sure that the pipes are kept straight. And that you can do in many different other ways. So here's a lecture to you. So make sure that whatever you're considering the welding is not your friend, but is your enemy. And you need to respect your enemy, because it can make your life very, very difficult. So this, by the way, the welding of aluminium is even more cumbersome, because in steel material, there's like a threshold loading, this equivalent loading, this one here. When you don't really see the fatigue anymore, you can make a safe assumption that this the fatigue life is like forever. So it's not going to fail in your lifetime, not even your children's lifetime. But in aluminium, it's going to happen eventually. Eventually it's going to happen. Of course, it can take years and years and years, but the aluminium is behaving in an unpleasant way in terms of fatigue. So it's even though that you can increase their fatigue life, but there is still fatigue life that will end one day. And now it seems to put the lights off. Don't know why. Okay, hey, this is another thing. Now, fatigue of a welded structure can be improved by using high or ultra-high strength steel. Remember what I just explained about this different steel material? So what about then you can use painting on other finishing technique like painting or something that takes these fatigue cracks away. Or you can use a post-welding treatment techniques. And post-welding treatment techniques are the one that are affecting the 2 things. So let me take myself back here. So they either, what you can do is that you can use maybe TIG welding to try to get rid of these initial cracks. This is one way you can do it. Or you can hammer this welded toy, try to get these initial cracks away. It's risky business because there's usually a lot of welding joints in a structure. There could be several kilometers, well, not if you think about that, the mobile machinery, but several, let's say 100 meters of welded joints. I used to be careful to do that. That's a lot to ask. But you can do something to this initial crack. You can try to take it away by using a TIG welding or hammering or something similar than that. Why is this behaving like that? Okay. Or another thing is that you can try to do something to these residual stresses. This is going to be very hard to do anything for that. But again, you can use a hammering to try to reduce that. And those are the called post-processing techniques. So which one out of the three is the way you can increase the fatigue life? Let me take myself back here. So using ultra high strength steel. Remember what we discussed about, how much difference they make. Use painting or another finishing technique. Painting is basically, you paint it, you don't see the problem. Maybe this is the way to go. Or using post-welding treatment techniques. And Socrative is on momentarily. How many students we have here? 7. It's still 7. Again, let's see how well we do here. No dancing, even if we're going to score 100%. Two students, there's quite a bit of delay. Okay. This is, by the way, I think that I need to close my lecture here because what follows is this large deformation. This is a lengthy explanation, which for sure I'm unable to do this in the 10 minutes. This is kind of funny story too. There's a lot of stuff that is educational, not just in terms of what it means in analysis wise, but something that tells a little bit about the life. Something that is by the way, here, this presentation is something that you see a lot of familiar faces. Not faces, but the familiar names here. Because I'm giving you an overview of the method that is heavily developed here in LUT University. You will see a lot of names that are being active in this development. Let me just show a little bit like examples. Not this one. Well, this is here is already Jussi Sopanen mentioned, and this is 2003. Let me get back. There is a Kimmo Kerkkäinen. You see that he is involved in the developments. Marko Matikainen, you may know him as well. Kimmo again, and so on and so forth. Okay, but this is going to be the story that I'm going to introduce you next week, Monday. So I'm not planning to get started in this today. Okay, back to Socrative. And we got 4 answers. I'm going to close it here. So 4 answers for sure is not enough. Okay, so it seems that it makes sense to have less students in round because it seems that you guys are then paying attention to my talk. Good, very nice, very nice. Okay, now let me close for today. And I know that I'm a little bit early to close it today, but still I want to close it today because there's no way that I can explain this large deformation in 10 minutes. Next Monday, I'm again here in the lecture room. If you want to see me face to face, take this opportunity. I'm here, and then next week we're gonna discuss about what was it? I need to take myself in the very beginning of today's lecture. So I promise that there is large deformation, then how to prepare yourself the written exam, and then the master thesis project. Yes, that's right. That's about it. And the master thesis work is not a part of the exam, but something I would like to share with you. Okay, with that, I'm going to close the streaming and